Okay, so now we're going to consider polyprotic acids. Polyprotic acids have more than one proton to titrate, and that's the difference. Poly meaning more than one. So there's at least two H pluses that can be titrated. Maybe there's 3, 4, so on and so forth. Okay, how do we handle these situations? Well, if you consider the titration curve for a polyprotic acid, this would be for a diprotic acid, specifically this one, okay? It's H2SO3, so it's a diprotic acid, 2 protons. You can oftentimes see 2 distinct equivalence points on the titration curve. This sometimes it happens, and sometimes they get blended together. But in this particular plot, you can clearly see 2 equivalence points here and here. Equivalence point 1 and 2 as this particular sample is titrated. Now you can see this type of behavior in the plot if the Ka1 is much, much, much greater than Ka2. And now we're talking about at least 10,000 times, 100,000 times greater. You can see this type of behavior. However, the closer the Kas are together, sometimes these two just sort of blend together and it's hard to distinguish 2 points. But here you can clearly see first proton being titrated, second proton being titrated. So I guess the key idea here then is if we're going to consider the titration curves quantitatively, we're going to consider the titration of these protons sequentially. In other words, for this particular acid, we'd have H2SO3 setting up an equilibrium because it is a weak acid to donate its first proton, making HSO3 minus 1 in the process, and that of course is governed by Ka1. And then in the second step, we can titrate off that second proton. Oops, just SO3 2 minus now. Alright, and of course that's governed by Ka2. Here are the values for these two. Can we compute the pH along the curve? I think that we can. Let's take an example problem, or this example problem, and try to work it. Again, I always like to come up with a sketch to remind myself of what exactly I'm considering, and I'm going to do that in this case. So what I'm going to consider is this burette and my sample down here. And I'm always going to put my pH probe here in my sample, and I want to know what is the pH of that solution equal to at different points on the curve. Now what is my sample? Well, it's going to be a 25.0 milliliter volume of my acid, and my acid here in this example was 0.1 mole per liter H2SO3 as discussed on the previous slide. My titrant is an NaOH solution, specifically 0.1 mole per liter, and I'm going to compute the pH at multiple points along the curve. My first point is also always before any titrant added. So my V added is 0 milliliters. I haven't added any of my titrant, have I? This is my V added. How much I drain, right? 0 milliliters. What do I have in this beaker if I haven't added any titrant? I just have a solution of my H2SO3, don't I? My weak acid. Now, that stuff can dissociate to donate a proton and make HSO3 minus 1. And of course, again, that's governed by the Ka1 expression, which is products over reactants, just like any equilibrium constant. So doesn't it make sense that before I drain any titrant, that the weak acid dissociation is what matters for the pH of this solution? Indeed, that's going to be the case. So all I'm going to need to do is write a Rice table with 0.1 mole per liter as my initial concentration, 0, 0, plus X, X, and X, 0.1 minus X, go to my Ka expression, X times X, divided by 0.1 minus X for my concentration of that, and that's equal to my Ka1. Now in this particular case, Ka1 is equal to 1.3 times 10 to the minus 2. We were given that in the problem. Okay, that's just a property of this particular acid. So rearranging and solving, we would have x squared is equal to 1.3 times 10 to the minus 3 minus 1.3 times 10 to the minus 2x. Moving that over to the left, I'd have 1x squared plus 1.3 times 10 to the minus 2x minus 1.3 times 10 to the minus 3 is equal to 0. This is the form that I can use my quadratic equation. So I would go ahead and do that. I'm going to make that choice this time because, again, my Ka is actually a fairly sizable number here. This is a reasonably strong weak acid, okay? So I'm probably going to need to do that. So I break out my quadratic equation. Maybe I use my solver function on my calculator, and I find my two roots or answers from the quadratic equation are negative 0.043 and a positive 0.0301. I'm not going to show that here just in the interest of time, okay? But because we can't have negative concentrations, I know that this one is bogus. Get rid of that. But this one seems like a reasonable answer for my x. If I look back to my rice table, I can see that that corresponds to the concentration of this ion. It also corresponds to the H plus concentration. Now remember when we worked this type of problem for polyprotics in the previous chapter? We decided that only the first dissociation was important. Guess what? That's going to be the same story here. This ion donating additional protons really doesn't take off to an appreciable extent. So because of that, the amount of H plus that we get from this first donation event dominates. And this is a pretty good approximation as to the total H plus concentration in this solution. So if I take the negative log of that number, I'm essentially solving for a good approximation of our pH. And that's what we're going to do. So I get my calculator, turn it on, negative log 0.0301. I get 1.52. So at this first point on this curve, before any of my NaOH is added, 1.52 is a pretty good indicator of that initial pH. That's how we handle the first point on a titration curve for a polyprotic acid. You just work the weak acid equilibrium problem, essentially treating the polyprotic acid as if it was a weak monoprotic acid. And that's the key. You just treat it like it donates a proton, work your rice table, solve for pH, and you're done. And it's that simple, okay? So that's before any titrant has added point A. Oops. So you know what? I should probably keep that picture. Maybe just put another piece of paper over on this side here, okay? So now I'd like to work another point on this curve. Maybe after a few milliliters of my titrant has been added. Let's just sort of pick a point. Let's say after 10 milliliters of titrant added. So 10 milliliters drained. How are things different? Well, now if I add my strong base, I'm going to start my titration reaction. I'm going to add some hydroxide. So I'm going to run a reaction where H2SO3 reacts with OH minus to make water when one of the H's combines with OH. But I'm also going to make HSO3 minus 1. So I'm taking one of the protons, but not both, because my titration proceeds in a sequential fashion. First proton, then the second. That's important, I guess, okay? So you got to be able to identify this key equation. But then after that, I'm actually going to do a similar thing to what I did before for these other titrations that we've been talking about. I'm going to work my ICF table. I'm going to figure out how many moles of everything I've got. how things change, and then where I'm at. So let's take a look at that. Can we compute the number of moles of OH that we add? Sure, all we need to do is multiply molarity times volume. My molarity was 0.1 moles per liter for my titrant. And in this particular case, I added 10 milliliters, which is 0.010 liters. So it seems like I've got 0.001 mole of my titrant added. Can I also compute the number of moles of my H2SO3? Well, if I multiply molarity times volume, I can compute moles of anything. So 0.1 molar, what's my volume? Well, it's 25 milliliters, that's 0.025 liters. So it looks like I've got 0.0025 moles of the H2SO3. So now, limiting reagent type problem as long 1 is strong. I'm going to run out of hydroxide first. I'm going to have 0 moles of that. I'm allowed to then react 0.001 moles of this stuff. I can't use any more because I run out of my strong base. And I'm left with 1.5 millimoles. So I've titrated some, but not all. I started off with 0 of this. I made 0.001 mole. And I've got 0.001 mole once the reaction's complete. So this is my inventory. I've made my inventory. I have to decide what I've got. And I notice right away I've got a buffer. Because I've got an acid and its conjugate base both mixed together in solution. I can use my Henderson-Hasselbalch equation. pH is equal to the pKa plus the log of the base divided by the acid ratio. Now, let's see, in the problem, well, okay, there's a couple things here, right? So the first one is which pKa to use, pKa1 or pKa2? Well, this proton that we're titrating is the first proton, right? So we're going to want to use pKa1. So back to the problem, you can see that the Ka is 1.3 times 10 to the minus 2. We need the pKa to put into our Henderson-Hasselbalch equation. So I'm going to have to take the negative log of that, so negative log of 0.013. And I get 1.88 for my pKa1. Really 1.89, but I'll put 1.88. Just didn't round, okay? So that goes there. And now I need the log of this concentration ratio between the base and the acid form. So this is, of course, the base, and this is the acid form. Because they're contained in the same volume, you can kind of usually take a shortcut when you plug back into the HH equation here for these titrations, where you just plug in the number of moles for each one. And that works because you divide both of them by the same number, okay? So I was just going to take that shortcut. So do 0.001 divided by 0.0015 equals that. Now I need to take the log of 0.66667 and then add that to 1.88. And I get 1.70 for my pH. So at this point, which is what, after 10 mils have been drained into the container, I get a pH of 1.7. Notice in our titration curve, because I'm titrating a weak polyprotic acid, a buffer forms in this region. We actually call this the first buffer region. There will be another one later. But this is the buffer region prior to the first equivalence point, in through here, after some titrant has been added, but that first proton hasn't been completely titrated off. We've got the mixture of the acid with the weak base. It's a buffer. We can solve for the pH of that buffered solution by using the Henderson-Hasselbalch equation with pKa1. You got to use pKa1 because we're still titrating that first proton. But other than that, it's relatively straightforward, okay? Let's move on then to another point on our curve. That was for the first buffering region. But now, the point I'd like to work in part C of this problem is at VEQ. Number 1, or the first equivalence point. So what happens at the first equivalence point? Now the volume for that should be at 25 milliliters, but let's just verify that's the truth, okay? So how do we do that? Well, we write our equation again, the H2SO3 plus the OH minus makes our water, and HSO3 minus 1. Do our ICF inventory. And we work the math. Earlier on the problem, it seemed like we had 0.0025 moles of our acid. Now let's figure out how much of this base we've got. Well, the concentration was 0.1, and if I multiply the molarity times the volume, that gives me moles. Well, that's 0.0025, isn't it? That's the same number of moles as the acid that I've got. So now we can see that we're going to consume 2.5 millimoles, end up with 0 of that. We're also going to consume 2.5 millimoles of this, end up with 0 moles of the strong base. We don't track the water. We start off with 0 moles of this. Now we're going to make 0.0025 mole. And we're going to end up with 0.0025 mole. This is characteristic of the first equivalence point of a polyprotic acid-base titration. We've run out of our OH minus because we've titrated that first proton off the H2SO3 completely and totally to make the HSO3 minus 1 anion. So we're at that point in the problem that we have to think what controls the pH. We don't have any of this. Water is not important. So the only thing to key in on then is this substance, right? But we have a little bit of a problem because this substance I like to call an intermediate form. And what I mean by that really is it's amphoteric. You may recognize that that ion can donate a proton to make H plus and SO3 minus 2. However, this ion can also act as a base. It could also accept a proton to go back to H2SO3 and hydroxide. So it's amphoteric. It could act as either an acid or a base, right? So you've got a solution of this intermediate form that can kind of go either way, like, well, what is it going to do, right? Well, it turns out that for the intermediate forms, we can use a relatively simple equation to predict or estimate the pH. And the pH for these intermediate forms is approximately equal to the average of the pKa's. So we simply average the pKa's, and that's a pretty good estimate of what the pH is for the solution of the intermediate form right there at that first equivalence point. So if I go back and I look at the problem again, okay, now pKa1, we said earlier, was 1.88. We haven't done this pKa yet, so I should probably do that if I'm going to work this problem at this point, right? So I need to do negative log of 1.02 e to the minus 7. Oh, it's a little under 7, yeah. So pKa2 is basically 6.99. Okay? So what this tells me to do is just to average those two. So I'm going to add 1.88 to that, divide by 2, and I get 4.43. That's the pH of my solution. So right here at this first equivalence point, after 25 milliliters is added, right there, 4.43 is a pretty good estimate of the pH, because all that's in solution there is that intermediate form. We've titrated off the first proton. Alright, so that's point C. Let's move on. Oops, need that. Let's see, point D. Let's see what's going on. Let's see. How about at 37.5 milliliters of titrant added? So we're working a new point. I think this one's going to be in the second buffering region. Let's see how we work it. So now our volume added to this sample is 37.5 milliliters. To figure out where we're at, you always go back to your inventory and you work your mole-based inventory first. You write the reaction, you write what you make. We do our ICF. Nothing really changes at first. You ask yourself, how much of this acid do you have? Well, you got 0.0025 moles of it, because it's 25 milliliters of 0.1 molar solution. Now you have to ask yourself, how much of the strong base? Well, let's see. The strong base was 0.1 moles per liter. Now we've added 37.5 milliliters, which is 0.0375 liters. So now I have 0.00375 moles of that stuff. Haven't made any of this yet. Becomes a limiting reagent problem. You run out of something. Here I'm going to run out of this stuff first. I only have 2.5 millimoles of it, and once I do, I'm out. Likewise, I can use 2.5 millimoles of this. And it looks like I'm going to have some of this left, won't I? I think I'll have what? 0.00125 left, right? After all's said and done. 1.5. I will make 0.0025 moles of this. So this ICF table looks a little bit different to us, doesn't it? Because now we've run out of this. We made some of its conjugate base, but we ran out of the acid. We no longer have a buffer between these two, because I don't have any of this. And I also still have some strong base. So I kind of have to ask myself, well, what really happens? I mean, I've got some of this strong base. Wouldn't it be at least conceivable that this substance, the HSO3 minus 1, might be able to react further? I mean, it's got this other proton. We started this off by saying it was diprotic. So So maybe that second proton will be forced to be titrated off by the presence of the strong base, and then I'll make SO3 2- as a result. So this is titrating the first proton up here on the top, and now we're getting into titrating the second proton. And if you've got excess strong base, turns out that will happen. So this reaction is very valid. We can still proceed through our normal organized approach, writing our ICF table with the initial quantities in moles. I've got 0.0025 moles of this stuff to use. I've also got a remaining quantity of 0.00125 moles of that. Now what's going to happen? Well, it becomes a limiting reagent problem again. It looks like in this case I'm going to run out of this one first. After I react 0.00125 moles, I'm not going to have any left. So I can only consume 0.00125 moles of this. That's going to mean that I have 0.00125 moles of that remaining. Likewise, I didn't have any of this doubly deprotonated ion at first, but I'm going to make some. 0.00125 moles of it should be produced if I go to the right. And that means once this reaction is complete, I will also have 0.00125 moles of this ion. So now I look at my ingredients in my container, and I decide that I've got 0.00125 moles of both of these ions, the SO3 2- and the HSO3 1. Could this also be a buffer? Indeed it is. Interestingly enough, during this titration, we have two different buffers form. The first buffer forms between these ions before the first equivalence point. And then after the first equivalence point, we have a second buffering region between these two ions. And this is typical for polyprotic acids. They can actually buffer in different pH regions as a result because they have different pKa's. But we learned that whenever we have a buffer, we can always use our HH equation, can't we? And in this case, since here we're titrating the second proton, we need to use pKa2 instead of pKa1. So we start with our HH equation, and we just plug into it. Now the second pKa of this acid was 6.99. We are given that in the problem essentially. Okay, that's the second pKa value. All I need to do to solve for this pH is to plug in some concentrations. And remember, since these are in the same volume, I can kind of use moles as a shorthand or shortcut. So I have 0.00125 divided by 0.00125. Oh look, these two will have the same concentrations, won't they? And earlier we said that the log of 1 is 0. So the pH at this very special point on our curve is pKa2, or 6.99, right about 7. So right here at my second equivalence, well that's not the second equivalence point, I'm at what, 37.5. So right here at 37.5, the pH of my solution is right around 7. Okay. This area then in through here is called my second buffer region. My second buffering region. First buffering occurs prior to the first equivalence point, and my second buffer region occurs between first and second equivalence point. This involves removal of the first proton. This involves removal of the second proton. But in either case, we can use, because we have a buffer, we can use the HH equation, okay? Alright, so that's my pH after 37.5 milliliters has been drained into the container. Got that one. Alright, so let's move on then. So now we're at section E of our curve. And this one's going to be right at the second equivalence point. So to consider this, we need to come up with a particular volume that we've added, and I'm going to say that's right at 50 milliliters, okay? So again, we start this exactly the same way we've been doing all these other times, okay? We titrate our weak acid with OH to make water and the HSO3. We start off with our ICF. Nothing's really different, right? We have 0.0025 moles of this. And now if I add 50 milliliters, I do my 0.1 mole per liter times 0.05. And I have 0.005 moles of my base. Okay. It becomes a limiting reagent problem. I use up all of this. Don't have any of it left. I use up half of this. End up with 0.0025 moles remaining after that first proton is titrated. Start with 0, make 0.0025 moles, have 0.0025 moles. Then we go to the second reaction. Titrate that second proton. If you have excess OH, you titrate the second proton. Make more water, make sulfite. Do your inventory. ICF, well, we started with 0.0025 moles of this that we made. We also had 0.0025 moles of this. So you can see where we're going with this. We're going to use both of these up. Minus 0.0025 minus 0.0025. We use them both up. We are at the second equivalence point now, aren't we? Now what do we make in the process? Well, we make 0.0025 moles of this ion. So that's what we have after all said and done. So you do your inventory, figure out what you got, and then you make a decision of what controls the pH. Now we don't have either one of these. Water doesn't change anything from 7. But look, we have this sulfite ion in solution, 2.5 millimoles of it to be specific. We know that this is fully deprotonated. It could potentially act as what? This is 2 minus. It could potentially act as a base, accepting a proton to make HSO3 minus 1, and OH gets produced. So couldn't I just write a rice table with initial concentrations of everything? I'll say 0 molar and 0 molar, and solve the rice table? That's what I'm going to do. So the hydrolysis reaction of the fully deprotonated form is the important reaction at the last equivalence point. You just have to figure out the molarities and work the problem. Alright, so if I was to ask what is the molarity of the sulfite here, we just need to figure out how many moles we've got. Well, that's 0.0025. Now I need to divide it by the liters of the volume. I got to figure this out, okay? Let's take a look. So I started with 25 mils on my sample, and now I've added 50 mils. So it looks like I've got 75 milliliters total volume, 0.075 liters. So I need to do 0.0025 divided by 0.075, and that equals to an initial concentration of 0.0333 repeating. I'm going to use some of this. I'm going to make some of these. Typical rice table stuff, right? And then at E, I'm going to have initial minus X and X and X. And you probably figured out what we're going to do with this now. We're going to solve our equilibrium constant expression, or go to our equilibrium constant expression K as being what? Our products over reactants. So X squared divided by 0.0333 minus X. Now we need a number to put in here for K, so we have to decide is it Ka, Kb, and I've got a base acting as a base. So it seems like it's Kb, and this is accepting the first proton, so I'm going to call this Kb1, because it's acceptance of the first proton. So I need to substitute a value in here, Kb1. Now, that's the Kb for this stuff, the SO3 2 minus. Now I have a little bit of a problem, because if I go way back to the original information that was provided to me. Actually, it's not even on that slide. It's here. What do I have? Ka1 and Ka2. I don't have any information about a KB, KB1 nor KB2. So the thing is that I kind of have to figure it out myself, what that KB1 is. And to help me do that, I remember that for a conjugate pair, Ka times Kb is always Kw 1 times 10 to the minus 14th. That only holds for a conjugate pair, though, right? So which substance do I want to compute the Kb of? It's this one, right? What is its conjugate base, or conjugate acid? This one. These two are conjugates. So the Kb of this substance times the Ka of this substance equals my Kb that I want, equals Kw. Well, the Kb times the Ka equals Kw. But these two are the pair that I'm interested in. So I need the Ka for this stuff, basically. So looking back, is that Ka1 or Ka2? Well, Ka1 corresponds to the donation of the first proton. Ka2 is the donation of the second. So I want Ka2, don't I? Okay? So basically, to solve for Kb1, I can say that Kw is equal to Ka2 times Kb1. And since Ka2 is 1.02 times 10 to the minus 7th, I can then rearrange and solve. So let's find my calculator here. So to solve for Kb1, I'd have to take my Kw, my 1e to the minus 14th, that's the value for Kw, and then divide it by 1.02 e to the minus 7th. And when I do that, my Kb1 equals 9.8 times 10 to the minus 1, 2, 3, 4, 5, 6, 7, 8. So 9.8 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. That's my Kb1. So I plug that number here, and then I work to solve. So as I'm looking at this, since Kb1 is so small, I think the assumption probably is going to work. And if I did that, then this x would go away, and x squared would equal this number times Kb1. So if I take 0.0333 and multiply it by 9.8 e to the minus 8, I only get 1 digit of precision, unfortunately, but I get 3 times 10 to the minus 1, 2, 3, 4, 5, 6, 7, 8, 9. On my calculator, only give me 1 digit of precision. Alright, so nonetheless, I'm going to need to roll with that. So now I'm going to have to take the square root of that, 3 e to the minus 9, and I get 5.47 times 10 to the minus 1, 2, 3, 4, 5 is equal to x. And what does that x correspond to? Did a lot of math work here, right? But got to make sense of it all now. It looks like it equals the concentration of this and also the concentration of OH. So if I want to compute the POH, I could take the negative log of that x value, and that would give me my POH. So of course that's what I'm going to do. So negative log of 5.47, second function e, minus 5. I get 4.26 as my POH. And then converting that to pH, taking 14 minus it, and we get 9.74. Okay, so what we just solved for then is the pH right there. at the second equivalence point as being equal to 9.74. Now there's only one more region on our curve to consider. This is this excess titrant region way out here, okay? How do we handle that? Well, let's think about what we get in our inventory if I added more than 50. So we just considered 50 milliliters. Let's consider 60 or 70, whatever number we want to, okay? What would happen? Well, if we drain more of our titrant into our receiving flask, we increase the number of moles of OH. So when we do our inventory, this number will no longer be 0. It'll be a positive number. And that will indicate excess titrant that we just can't get rid of, can we? Can't titrate it because all of our protons from the acid are gone. Because we have excess titrant, the OH concentration in that final solution is primarily determined by whatever that number is. So this point would actually work exactly the same to the excess titrant on the previous example we saw for the strong acid base or the weak acid base. You just figure out how much excess OH you've got, how many excess moles that just can't be titrated, convert that to a molarity or a concentration. That's your OH concentration. It's a really good estimate of your hydroxide concentration at that point. Take the negative log of that. That's your POH, and then solve for pH. You're done. It's as easy as that, okay? So I'm not going to actually, in the interest of time here, we'll run out of time for today. So I'm not going to work that point, but it's worked exactly the same. You just build your inventory, you find a non-zero number here. This reaction is no longer even important because, again, the amount of OH that you get from the excess titration or the over-titration is usually far greater than anything you get from the hydrolysis of this. So take the excess moles, convert to a molarity, compute your POH and then your pH, and you're done. So it's as easy as that, okay? So we've considered now titration of a polyprotic weak acid. Remember what we said? Before any titrant was added, the dissociation of the weak acid was what was important. We treated it only as a monoprotic weak acid. Additional proton donations were not important. Then we moved into a first buffer region where we were titrating the first proton. Remember, it was sequential. We could use Henderson-Hasselbalch equation there to compute the pH along with pKa1. Then we reached the first equivalence point. That was the intermediate form where we had a beaker of essentially the amphiprotic substance. It could donate a proton, it could accept. And remember, the pH there was found by the average of the pKa's. Then we moved into the second buffering region, where we were finally getting to titrate that second proton off. But we still had a buffer because we had a mix of this ion along with SO3 2-. That was our second buffering region. Can use Henderson-Hasselbalch again with pKa2 there. Then, at the second equivalence point, that's the example that we just worked. The key reaction there was the hydrolysis reaction of the fully deprotonated form, accepting a proton and making some OH. So again, the pH will be basic at that second equivalence point when you titrate a weak or polyprotic acid. And then the last region was excess titrant. This is where we've over-titrated. We've added too much of the strong base. And when we work our quantitative inventory, we would find that we had some of this left if we did that point. Okay, we didn't show that example, but we'd find that this was non-zero. There'd be some number of moles of OH left over that you just can't remove through titration. Figure out how many moles excess you have, convert it to a molarity, take the negative log, and that's your POH. From there, you can easily get pH and solve for the pH of the solution. So we've considered weak monoprotic acids, and now we've considered weak polyprotic acids. We don't have to be scared by it. And in fact, the questions kind of become fun after a while because they're very logical. All right, see you next time.